Okay, welcome everyone. This is a lesson today on how to create the unit circle. Normally I would teach on the whiteboard, but this is a really difficult unit to do on the whiteboard, so we're going to do it on paper. The unit circle, which looks like this is what your final copy is going to look like. Mine is a bit beat up, it's really old. Is your Bible for the first part of trig, definitely, and to a lesser extent the second part of trig. If you're in school in Alberta or in BC, you will have to use the unit circle on a test. However, they don't actually give you a unit circle, so you have to learn to make one on your own. But it's not that hard, and we're going to learn how to do it today. So the unit circle is based on three special triangles. Okay, it's based on the 30-degree, the 45-degree, and the 60-degree triangles. Those are the three special triangles. We're going to start with the 30-degree. So let's make a triangle on the Cartesian plane that is an equilateral triangle. Okay, so what we have is an equilateral triangle with side lengths 2, and if it's an equilateral triangle, then the angles, all three angles, have to be 60 degrees. That's the textbook definition of an equilateral triangle. Okay, now in order to make this fit onto the unit circle, the 30-degree triangle, the first thing we're going to do is we're going to cut this in half. Okay, when we cut it in half, we create a 90-degree triangle. So now we have 30 here, 60 here, and 90 here. Now we have our right angle 30-degree triangle. This is 2, the length is 2, this length is 2, but I've cut it in half, so now this length is 1, okay? What we don't know is what this length here is. So what we're going to do is use Pythagorean theorem to figure it out. So we have 1 squared plus b squared, this length here is going to be b, is equal to 2 squared, which gives us b squared equals 4, subtract 1, b squared equals 3, so b is equal to root 3, okay? So that's this length here. So now what we're going to do is look at the three main trig ratios for this 30-degree triangle. So we have 30 degrees here, 60 here, and 90 here. When we're working in trig on the Cartesian plane, angles are always measured from the origin, never from up here, okay? So we always measure the angles from here. So this is a 30-degree triangle because it's 30 degrees here at the origin. Okay, so the sine of 30 degrees is equal to the opposite 1 over the hypotenuse 2. Okay, the cosine of 30 degrees is equal to the adjacent root 3 over the hypotenuse 2, and the tangent of 30 degrees is equal to the opposite 1 here over the adjacent root 3. Now, when you get up into calculus and that, they don't care that much about the denominators not being rational, but in Math 30, they do typically want you to rationalize those denominators. So we do that by multiplying the top and the bottom by root 3, which gives us root 3 over 3. Okay, so those are the three ratios for the 30-degree triangle. Now, what we're building is this here. So on graph paper, could use a ruler for this, but that's okay. On graph paper, we're building the unit circle. Now, why is it called the unit circle? It's because it's a circle with a unit of 1. It's a 1-unit radius circle, okay? So that's why it's called the unit circle. So this is what we're building right there, okay? Now, I know that's kind of small, but it's to make a point. See, what we're doing is we're putting those three triangles into this first quadrant, right? Okay, so on a bigger sheet of paper, here's what that looks like. We have, okay, there's the center of my circle, and there's my circle there, and this is 1 unit right here. Okay, so from there to there, that's 1 unit, And of course, if this is 1, then this is 1 as well, right? Because the radius is the same no matter where it's drawn in your circle. And there's another 1. Okay, so this is your 60-degree circle, or a 60-degree triangle. That's your 45-degree triangle, and that's your 30-degree triangle. Okay, so this is what we're making. So right now, if I wanted to draw a circle around this, I have a problem because the radius of this triangle, or the hypotenuse of this triangle, which is the radius of the circle, same thing, is actually 2 units when I need it to be 1. So what I need to do is I need to cut this thing down to size so that it will fit inside that unit circle, that 1, this needs to be 1, okay? So what that means is that I'm going to cut this exactly in half, right? And I'm going to do it proportionally, because if I don't do it proportionally, I'm not going to have a 30-degree triangle anymore. It will be some other kind of triangle. So I'm cutting it in half, which means all of these 3 lengths are going to get cut in half. So this 1 is now 1 over 2. This 2 is now 1. That's what we need this hypotenuse or the radius to be. And this root 3 that was here is now root 3 over 2, right? Okay, so now what's happened to my ratios? Well, you can guess that they need to stay the same. They have to stay the same because I haven't changed the proportions of this triangle. The proportions have stayed the same. It's just gotten smaller. So now the sine of 30, here's how this works now. The sine of 30 is opposite 1/2 over the hypotenuse 1, but because the hypotenuse, which is the denominator of this thing, is 1, we don't write it. Okay, we could, but we don't, right? Because you never put a 1 in a denominator when that denominator is 1. Okay, the cosine of 30 degrees is root 3 over 2 over 1. But again, we don't have to put that 1 down. It's not necessary. The tangent of 30 degrees is 1 over 2 over root 3 over 2, right? But this is obviously not how we want to leave it. So we get rid of the denominator since they're the same, which leaves us 1 over root 3, which is what we had up here. And when rationalized, we get root 3 over 3. So everything is exactly the same, which it needs to be. It has to be, or else this doesn't work, okay? So now, this point here is this point here on the circle, on the edge of the circle, okay? If we look at this here, that's the point here that is on the tip of that triangle, okay? So now this circle that I sketched in here before, which had a radius of 2, is now the proper size. It now has a radius of 1 unit, okay? So again, this here would be 0, 1 on a Cartesian plane, and this point right here is going to be 1, 0. Does that make sense? So let's put it on our unit circle here. Now this circle has accurately drawn angles. So this actually is 30 degrees right here, okay? Okay, so let me write the 30 degrees here. Now this point, again, is this point right here in the Cartesian plane, okay? That point has an x-coordinate of root 3 over 2, which is approximately equal to 0.866. And this, the y distance to that point, is 1 over 2. Okay, so we're going to put that here because those are the coordinate values of that point, root 3 over 2, comma 1/2. Okay, so that's your 30 degree. Now, if somebody asks you, what is the cosine of 30 degrees? All you really have to do is look at that x value, because this x value, root 3 over 2, is this distance here, which is the adjacent leg, okay? You don't have to worry about the hypotenuse. Yes, this is over 1, root 3 over 2 over 1, but you don't need the 1 because the 1 is irrelevant. So the cosine of 30 degrees, the cosine of any of these angles, is simply the x value of these coordinate points, which we're going to fill all of them in eventually, okay? So that's why the unit circle is so powerful, because you can just lift your answers directly from the unit circle itself. And I'll show you how to make one so that it's really quick and easy, all right? Okay, so the next thing we're going to look at is the 45-degree triangle. Actually, no, we're going to do the 60 next, and then we'll do the 45. Okay, so the 60-degree triangle, we take the same, here, let's use a different sheet of paper so that we have more room. Okay, so for the 60-degree, we're going to do, again, on the Cartesian plane, and we're going to set up the same triangle that we set up before, except we're going to set it up like this. So again, this is an equilateral triangle with side lengths of 2. So right angle triangles have 2 sides and a hypotenuse. Other triangles have sides, or rather, right angle triangles have 2 legs and a hypotenuse. And all other triangles have sides. And it's just kind of a terminology thing. Okay, so these are sides, they're not legs. Only right angle triangles have legs. Now what we're going to do is, once again, as we had before, all these side lengths are 2. We're going to cut this in half because we need this to be a right angle triangle. When we do that, this stays 2, this becomes 1, and we know from the Pythagorean math that we did on the other triangle that this length here has got to be root 3. Okay? So now let's find out our ratios. So the sine of 60 degrees is opposite root 3 over hypotenuse 2. The cosine of 60 degrees, let me write that down, is 1 adjacent over 2. And notice these are the reverse of the sine of 30 and the cosine of 30, right? The cosine of 30 is the sine of 60 and the sine of 30 is the cosine of 60. It makes perfect sense because the corners that you're working from are just the opposite corners, right? Opposite is now adjacent, adjacent is now opposite. So it makes perfect sense that those are just the reverse of each other. And that causes confusion when you're setting up your, when you're making your unit circle, but I'm going to show you how to not get caught up in that confusion, okay? And then the tangent of 60, this one's a little bit easier. We don't have to rationalize because the root 3 is on top this time, not on the bottom. So it's just root 3. And again, because that denominator, this time it's the adjacent leg, is 1, we don't have to worry about writing that 1 because it's in the denominator. Okay, so once again, we have a problem though because this triangle is too big, right? Okay, I've made it so that it's actually a radius of 2 when it needs to have a radius of 1. So we're going to cut this down to size, which means we're going to cut it exactly in half. So this length here becomes 1, that's what we need it to be. This length is now cut in half, so we divide by 2, it becomes root 3 over 2. And this length, which was 1, becomes 1 over 2. So now let's look at our ratios again. What's happened? Okay, well, the sine of 60 is the opposite root 3 over 2 over the hypotenuse 1. And once again, we don't need to worry about writing down that hypotenuse length because it's 1, okay? And this is why the xy coordinate points are all you need to know what the cosine and sine values of any of these angles is. Then the cosine of 60 degrees adjacent is 1/2 over hypotenuse 1. And the tangent of 60 degrees, okay, like we did before, it's a little complex fraction, nothing too difficult though. Okay, so we have the opposite over the adjacent, or sine over cosine, we'll get into that a bit later. These go away, so we end up with simply root 3, which is exactly what we've got up here, okay? They have to be the same, that's what trig is all about. If the proportions of the triangles don't change, then the ratios won't change either, okay? So what we've got is this point is a point on the edge of the circle. So this point right here, we'll label it in a sec. And that point has an x coordinate value of 1 over 2 and a y coordinate value of root 3 over 2. So these are just numbers, right? This is 0.5, this is 0.866, or almost 0.9. Okay, so that is this point right here on the edge of the circle. We're going to draw a line down to the x-axis for this, like so. Okay, we'll call this 60 degrees, that's what it is, and we'll label it with its coordinate value, 1/2 and root 3 over 2. Okay, so if somebody wants to know the sine of 60 degrees, you just go to the y value, because the y value is this, which is the opposite, okay, over the hypotenuse, which you know is 1. So let's stop there for a sec and let's talk about the equation of the unit circle. So again, if this was graph paper, here would be your next lines, right? If we were going 1 to 1 like that. Okay, so you can see that this 0.866 that I'm talking about, which is root 3 over 2 is equal to approximately 0.866. That distance is nearly 1, like it's 0.9, so it's really close to 1, which is what this is. So this is 1, 0, and up here we have 0, 1, right? And this point here, it's just hand drawn, so it's not perfect, but this is 1/2 of the distance to here, right? And up here it's 0.866 of the distance to here. So these are the same triangles, they're just positioned differently, okay? For the 45 degree, we've got the opposite leg and the adjacent leg are the same length, okay? It's the definition of a 45 degree right triangle, always has to be isosceles, okay? So what is the equation of the unit circle? It's this, okay, x squared plus y squared equals 1. So for circles, this standard equation it looks like this: x minus h all squared plus y minus k all squared equals r squared, okay? HK is the center of your circle, and r squared is simply the radius of the circle squared, the radius squared, all right? So if I wrote out something that looks like this, x minus 4 squared plus y plus 2 all squared equals 9, I would have a circle centered at 4, -2, right? Always opposite signs when something is embedded inside the function, and the radius of this circle would be 3, okay, the square root of this. Now, this one here could be written like this, but of course we wouldn't do it, right? X minus 0 all squared plus y minus 0 all squared equals 1. I mean, you wouldn't do it, but that's where this is all coming from, okay? So this is the equation that we're building, and the new curriculum does have some unit circle work where you're expected to determine whether a point given is on the unit circle, because there's, you know, there's an infinite number of points on the circle, right, all the way along here. We're only concentrating on 3 in each quadrant, and then at the 4 you know, the north, west, east, south points, okay? Okay, so now we'll go on and we'll do the 45 degree. Okay, so the 45 degree triangle is a right isosceles triangle, and we set it up like this. Okay, so we have 45 degrees here, we have 45 degrees here, and our leg lengths are 1. Okay, that's how we start the setup. All right, now, hypotenuse, what's the length? Again, we use Pythagorean theorem. 1 squared plus 1 squared equals c squared. 2 is equal to c squared, so c is equal to root 2, okay? So this is root 2, great. Now let's look at our ratios. Okay, so the sine of 45 degrees is 1 opposite over root 2. Okay, now we need to rationalize that, don't we? So we multiply by root 2 over root 2, which gives us root 2 over 2. The cosine of 45 degrees is the same, right? Because we've got adjacent 1 over hypotenuse root 2, and when we rationalize, it's root 2 over 2. And then the tangent of 45 degrees, this is everybody's favorite, is 1. Okay, 1 over 1 is simply 1. Okay, so once again though, the triangle is too big. It has to have a radius of 1. So what we do is we divide by root 2. Okay, this is why we divide by root 2, because we need this to be 1. And happily, all of those denominators inside the quadrants end up being 2's because we have to rationalize. So the root 2 over root 2 gives us 1. 1 over root 2 we know is root 2 over 2. So let's just put that here. And this same thing, 1 over root 2, sorry, is root 2 over 2, so we'll just put that down right away. Okay, so now what are my new ratios? Well, we already know they haven't changed, but let's see how that looks. So the sine of 45 degrees is root 2 over 2 over 1. Once again, we do not need to write that 1, okay? Cosine of 45 degrees, same thing. We have root 2 over 2 over 1. We do not need to write that 1, okay? And the tangent of 45 degrees is root 2 over 2 over root 2 over 2, and we already know that anything that is any fraction where the numerator and the denominator are the same is equal to 1. So there's that. Okay, so now let's keep building this unit circle. So what we've got now is we have right in between here, right in between the 30 and the 60 is our 45-degree triangle, okay? And we know that this point right here is on the edge of the circle, okay, that's right here, and that point has an x coordinate length of root 2 over 2 and a y coordinate length of root 2 over 2. Okay, so we're going to put that out here. There. Okay, now that's the basic foundation for the unit circle. If you understand the consequences of these numbers, if you understand how they work, why they work, then you're 80% of the way there, okay? Because understanding that, okay, what is the sine of 45 degrees? The y value, root 2 over 2, because we're just taking this length, which is this here, it's just your y distance, right? Remember, this is sitting on a Cartesian plane. This is 0, 0. This is 1, 0. And this up here is 0, 1. So these are just coordinate points, and these are just numbers. Root 2 over 2 is equal to about 0.707. So they're just numbers, so don't freak out with all the radicals. You get a lot of radicals in trig because you're working with right angle triangles, and so you're working with Pythagorean theorem, which involves squares and square roots, and there aren't very many right angle triangles where, or rather, there aren't very many instances where a natural number squared, okay, so this one, for example, 3 plus another natural number squared equals a third natural number squared. This one happens to work out, okay, 9 plus 16 equals 25. But if you've got a triangle that's, I don't know, let's say 4 here and 5 here, let's take a very simple example. The hypotenuse will not be a rational number, okay? 4 squared plus 5 squared equals c squared. 16 plus 25 equals c squared. 16 plus 25, okay, take it off to the side if you need a little help getting it figured out, is 41, okay? 41 equals c squared. Well, 41 is not a perfect square. So in order to have this recorded as an exact value, we have to simply put root 41, okay? And then sometimes you're going to have to rationalize that because it's going to end up in the denominator. If you ended up with something like c equals root 12, well then you would reduce that to 2 root 3, okay? Just making sure that your radicand never contains a perfect square factor, okay? So this is why we end up with so many radicals in trig, because this situation where a natural number squared plus another natural number squared equals a third natural number squared is pretty uncommon, okay? So that gives us the main part of the unit circle. So what we're going to do now is we're going to go around and fill in the degrees. Now hopefully by now you know what the main degrees are, but there's a nice little trick for remembering what they are, and I will give you that trick later on when I show you how to make this thing quickly. So we're just going to go around and we're going to put in our degree values, okay? So 120 there, 135 there, 150, this of course is 180, then 210, 225, 240, 270, 300, 315, 330, and finally 360. Okay, now the next thing we're going to do is fill in the coordinate points for the rest of the circle. This is really important. A lot of students reckon that if they can get their first quadrant sorted and get it, you know, written out and drawn out on the paper, then that's enough, and they can just use that to do all their work. But I highly discourage that, okay? You should really have all 4 quadrants filled in. And when we get to a point where I think where what is necessary for the unit circle, the minimum amount necessary on it, when we get to that point, I'll let you know. And anything beyond that is kind of up to you, okay? And certainly anything beyond that would be good to have for your main unit circle for when you're just practicing, doing homework or whatever. So over here, remember, this is a Cartesian plane, right? This is your x-axis, this is your y-axis, which means that over here, x is negative, yeah? But up here, y is still positive. Now, the 120-degree angle is a 60-degree triangle, okay? If we drew down a triangle for this, it would be the same shape as this one, same size, same coordinates, everything. But over here, x is negative, isn't it? So when you're filling in your other 3 quadrants, all you have to do is look on the other side of the axis and see what the numbers are, and then just adjust your negatives and positives accordingly. In other words, all your angles mirror over the axes, okay? So this angle mirrors this one mirrors that one. So just look over, see what's written there, and just adjust your negatives and positives as required. Look over there, this one mirrors this one. So negative root 3 over 2, comma 1 over 2. We know from basic coordinate geometry that this is negative 1 comma 0. This one mirrors that one, but in this quadrant, both x and y are negative, right? That one mirrors that one. This one mirrors this one. And this one, again, coordinate geometry, we know this is 1, the radius of 1, it's going down, it's not going left or right, so it's 0 for x, negative 1 for y. That one mirrors that one, so positive 1 over 2, y is negative, yeah? Root 2 over 2, negative root 2 over 2, positive root 3 over 2, and negative 1 over 2. This here is negative 1/2 because it's going down, right, from the x-axis, all right? So that's it. Okay, we're almost there. This is just about what you're going to need for your basic unit circle, but we have to talk about radians. So radians can be a little difficult to understand, but the thing to know about them is that they're just numbers, okay? And they are simply another way of expressing the size of an angle. So what is the size of a 180-degree angle in radians? It's pi, okay? This is pi radians. So if this is pi radians, which is approximately equal to 3.14, we all know that pi is equal to about 3.14, then this up here, if this is pi, well, this must be half of pi. 90 is 1/2 of 180, right? So this is pi by 2. That makes sense, right? This is 0. Now, what is 30 over 180? Well, if you forget your radian values, then you can do this. 30 over 180, okay? Lop off the zeros, gives you 3 over 18, which reduces to 1 over 6. So that means that this line here is 1/6 of the way around to that line there, right? So in a positive order of rotation, this line here is 1/6 of the way around to that line. So this one must be pi by 6, okay? This one here is pi by 3, and this one is pi by 4. Now, if you've done a little bit of trig, you should be pretty comfortable with those numbers by now. If trig is new to you, then I will explain a little bit more when I show you how to fill one in quickly, how these numbers turn out the way that they do, okay? So now let's talk about how to quickly make a unit circle, and then we'll finish filling in all those pi bys. So what we're going to do, you're going to need at least a 1/4 sheet of paper, okay? A 1/2 sheet is better. If you have a ruler to hand, great. Don't really need one though. And you're just going to try to be reasonably neat though, okay? So I want you to draw 3 lines in each quadrant like this. Again, try to be neat because it'll help you later on when you're trying to see what you're doing. And then we know this is 0, 0. We know this is 0, 1, okay? You got to memorize that. If you don't know that, you're kind of in trouble anyway, but, and this is 1, 0, okay? You don't need to put points, it's fine. You don't even need to draw triangles, you just need the lines, okay? Now, what you're gonna do is put coordinate pair brackets at the end of each line. And then start at this 0 or start at this 0 and then count up by 1. So you're gonna go 0, 1, 2, 3, or go 0, 1, 2, 3. It works either way, okay? And then you're just going to fill in everything around it. So the denominators are 2. Unless your numerator is a 1, your numerator gets a radical sign. Okay, and this way you can't forget what goes where. Because students generally remember this root 2 over 2, root 2 over 2, but they often get these two mixed up, and now you won't get, that won't happen, okay? You won't get it mixed up anymore. So 0, 1, 2, 3, or 0, 1, 2, 3, okay? We'll get you there. All right, now, to fill in the rest of it, we just saw how that happens, okay? You're just going to write, you're just gonna hop over there, you're gonna have a look at what's going on the other side of the axis, and you're going to fill in your values. X is negative here, Y is positive. So this is what you do to get it done quickly, right? Look up there, X and Y are both negative. So just copy those numbers, but make both values negative. And here they're both, X is positive, but Y is negative. And positive root 2 over 2, negative root 2 over 2, root 3 over 2, and negative 1 over 2. Yeah, that's it, okay? Now, when you fill in your degrees, hopefully you already know this is 30, this is 45, and this is 60. This is 90. Almost all of you will know this by now. So go ahead and fill those in, but then what you're going to do is go the rest of the way, all the way around, okay? So you're going to use this little rhyme to help you out. When you leave an axis, okay, you're leaving an axis, or when you're heading towards one, you add 30, and in between you add 15. Always count, okay? Always do the adding, because you know this is 180, okay? Maybe you put it in beforehand, that's fine. If you stop counting or if you stop adding because you know this is 180, then it's not going to highlight errors that you might make elsewhere. So always do the addition even though you think you know what it should be. So 90 plus 30 is 120, plus 15, 135, plus 15 is 150, plus 30 is 180, plus 30 is 210. So what I'm saying is, if you make a mistake and put 145 here, then you're going to end up with 160 here, and you're not going to end up with 180 here when you add 30. So always add, because that will help to highlight any errors that you might have made elsewhere, okay? So adding 15 gives us 225, adding 15 gives us 240, adding 30 gives us 270, adding 30 gives us 300, add 15, and add 30. Okay, nearly there. Now, your pi values, your radian values. Start with your 30 degree and label it as pi by 6, using that little trick to figure it out if you happen to forget, okay? Now, you're going to skip all your quarter lines as you make your way around. So, pi by 6, and you're going to count in 6. So the advantage of doing it this way is that you can count ones. You can count up by 1, always adding 1, okay? So this is 1 pi by 6, this is 2 pi by 6. 2 pi by 6 reduced is pi by 3. So reduce as you go, all right? 2 pi by 6 is what we had. This is 3 pi by 6. 3 pi by 6 reduced is pi by 2. 3 pi by 6, 4 pi by 6. 4 pi by 6 reduced is 2 pi by 3. Skip your quarter line. This was 4 over 6. This is 5 over 6. So 5 pi by 6. This is 6 pi by 6, which is pi, right? So what you'll notice is that the sixth lines next to your y-axis, they reduce. The 6 lines next to the x-axis don't, okay? And the 6 lines next to the y-axis are actually thirds, okay? But all you gotta do is go 1 pi by 6, 2 pi by 6 reduce, 3 pi by 6 reduce, 4 pi by 6 reduce, skip that quarter line, 5 pi by 6, 6 pi by 6, this is 7 pi by 6, notice we're always adding 1, skip the quarter line, 8 pi by 6 is 4 pi by 3, 8 pi by 6, this is 9 over 6, which is 3 over 2, which makes sense, that's 1.5. 9 over 6, 10 over 6 reduces to 5 over 3. 10 over 6, skip your quarter line, 11 over 6. 12 over 6 is 2 pi. Right, almost there. Okay, now you're going to count your quarter lines. So this is, again, to fill in a unit circle quickly when you walk in to write a test. Shouldn't take you more than a couple of minutes. If you practice one every day as you're having your morning breakfast cereal, your eggs, just quickly draw one out. By the time you're writing your test, you should be able to do one in about 2 minutes. Okay, this is 1/4 of pi. So that's 1 over 4, pi by 4. You're going to skip all your 6 lines, but in order to keep adding 1, you're going to also take into account these ones as you go. So this is 1 over 4, this is 2 over 4, but notice it's already there. 3 over 4. 4 over 4, already there. 5 over 4. 6 over 4, already there. 7 over 4. And 8 over 4, already there, okay? For a test, this is pretty much your basic. This is what you need. Anything less than this is not enough, okay? You gotta have this much on there. Now, let's get those things onto our good copy here, okay? So remember, when we're doing our pi radians, we're adding in sixths. So pi by 6, 2 pi by 6, 3 pi by 6, 4 pi by 6 reduced, 5 pi by 6 does not reduce, 6 pi by 6, 7 pi by 6, 8 pi by 6 reduces, 9 pi by 6 reduces, 10 pi by 6 reduces, 11 pi by 6, 12 pi by 6 or 2 pi. All right, then we're going to do our fourths. So this is 1 pi by 4, 2 pi by 4. This time you skip all your 6 lines. 2 pi by 4, 3 pi by 4. 4 pi by 4, it's already there. 5 pi by 4. 6 pi by 4 is 3 pi by 2. 7 pi by 4. 8 pi by 4 is 2 pi. So you can see how relatively quick it is to fill it in once you understand that you just have to count. Count and look. Count and copy and look. That's really all you have to do. It's just that first quadrant you got to get filled in kind of more or less from memory, okay? But even there, you're just going to go 1, 0, 1, 2, 3, or 0, 1, 2, 3, all right? And that makes it easy. Now, the unit circle is designed to show us cosine and sine, okay? It is not really designed to show us tangent, but hopefully you already know this. Tangent theta is equal to sine theta over cosine theta, okay? This is another way of saying opposite over adjacent, or y over x. So if you want to know what the tangent values are of any of these angles, all you have to do is put the numerator of the y value over the numerator of the x value. You don't have to worry about the denominators because in every single pair, the denominators are the same, so they're going to cancel anyway. So what I like to do on my unit circle, certainly my main one, is just scribble in my tan values. Tan here is this over this, so root 3. Tan here is so easy, right? Everybody knows that it's 1. And tangent here is root 3 over 3. Okay, we saw that earlier when we put the y value over the x value. It's 1 over root 3, which we rationalize to root 3 over 3. And that's it, okay? So this is basic. This is what you need to know. Now, some other things that we can add to this to improve its usefulness is the cast rule. Okay, you might have heard about this. The cast rule is simply this. I mean, it's useful. I don't use it very much myself, but it is useful. The cast rule is an acronym for which ratio is positive in which quadrant. Okay, so in this quadrant, only cosine is positive. Okay, so your x values are positive. In this quadrant, all your ratios are positive, which is why you have A. So cosine is positive, sine is positive, tangent is positive. In this quadrant, only sine is positive, okay? Because cosine is a negative adjacent over a positive hypotenuse. Okay, this is something I need to mention now. The hypotenuse is positive no matter which quadrant it's drawn in, okay? The hypotenuse is always, 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 always positive. So don't get that mixed up. Don't think because it's going down or it's leaning to the left or whatever that it's negative. It's not. The hypotenuse is always positive, okay? So that's why cosine is negative here. We've got a negative adjacent over a positive hypotenuse, right? Down here, when we put a negative opposite over a negative adjacent, we end up with a positive value, which is why tangent is positive in this quadrant, okay? Cosine is the only one positive in this quadrant because the opposite over the hypotenuse, sine, will be negative because this is a negative value, this is a positive value. Cosine, positive over positive, that's why cosine's positive in that quadrant. And finally, your tangent value, opposite is negative, adjacent is positive, therefore tangent is also negative in this quadrant. Okay, now a couple of other things that we should talk about quickly, and then we can wrap this up. Your reciprocal identities. So sine theta is equal to 1 over cosecant theta. Cosine theta is equal to 1 over secant theta. And tangent theta is equal to 1 over cotangent theta. So the way they're related, let's talk about this for a sec. So sine theta is opposite over hypotenuse, right? Cosecant theta is defined as hypotenuse over opposite. Cosine theta is equal to adjacent over hypotenuse, and secant theta is equal to hypotenuse over adjacent. Finally, tangent theta is opposite over adjacent, and cotangent theta is equal to adjacent over opposite. So back in grade 10 or something, when you learned about this to begin with, you learned about the ratios with the little SOHCAHTOA mnemonic, okay? This works great for sine, cosine, and tangent, and then the others are just, you just flip them, okay? Hypotenuse over opposite, hypotenuse over adjacent, adjacent over opposite. Nobody gets this one mixed up, okay? Everybody understands that tangent and cotangent are related, but these two tend to get mixed up a lot and it costs a lot of marks. So what you want to do is, there's two ways to remember it. So sine and cosecant are related, but they have opposite letters. See, they start with opposite letters. Cosine and secant are related, and they're also with opposite letters. So that's one way to remember it. The other way to remember it is that every pair of these functions has only one co between them. Okay, so this is cosecant, this is cosine, and this is cotangent, right? So they only have one co between them, which is another really good way to remember it. Okay, so I think that's it. I'm trying to think if there's something else I want to talk about here. One other thing, and that is the radian values when pi isn't involved. So remember we talked earlier about how radian values, so 5 pi by 6 for example, is a radian measure of this angle size right here, right? But it's also 5 pi by 6, if we put it on a calculator, okay, if I go 5 pi by 6, that's equal to 2.62 approximately. But again, because pi is in there and because pi is irrational, this number here is, by necessity, it's something that needs to be rounded. So by definition, it's actually inexact because you got to round it somewhere because it continues to divide infinitely, okay? It's an irrational number. So this 5 pi by 6 is a rational, or not a rational number, but it's an exact value, okay? It's an irrational number, but it's an exact value if we write it like this. But it helps to remember that there's still just numbers in the end, okay? They're real numbers that can be put on a number line, but they're irrational. So it helps to know that pi by 2 is equal to about 1.57 radians. So you could say that 90 degrees is pi by 2 radians, but you could also say that it's 1.57 radians. It's really saying the same thing. Okay, 3 pi by 2 is a way of saying 4.71 radians. Again, this is approximate. And here, 6.28 radians is approximately 2 pi radians. And then one last thing. If you were asked where 1 radian was, could you figure that out? Do you know where that is? Well, remember that this is about 1.57 radians. and that's 0 radians, right? So if we divide this into thirds, like so, then this is going, so this is 90 degrees, this is going to be about 60 degrees, this is going to be about 45, and this is going to be about 30. So we've divided this into thirds, okay? So, we haven't divided it into thirds, we've divided it into quarters. So let's just get rid of that. So now this is divided into thirds, okay? So here we have this is pi by 6, because remember it's all the way around to here, right? This around to here is pi. This is pi by 3. So this is 1/3 of the way up to here, and this is 2/3 of the way up to here. This is, so 1 radian is equal to approximately 57 degrees. It's just shy of 60, which makes sense if you take 1.5, 1.0, 0.5, and 0, just roughly rounded. 0 is here, 30 degrees is here, that's 0.5 radians. Okay, 1 radian is about 60 degrees, so we have 0.5 here, 1 here, and 1.5 approximately here. So it just gives you a sense of where your radian values that don't have pi in them, where they fall, okay? So if you're doing a question and you end up with something that is 4.32 radians, like, do you know which quadrant that should be in? Well, it should be in this quadrant here, because here we have 3.14 radians, and here we have 4.71 radians. So 4 radians is going to be in this quadrant here, all right? So in the comments, let me know if you have any questions. I'll try to get to them as quickly as I can. And that's it for today. So hopefully that will help you when you write your test, and we will see you again soon.